Okay, it's demonstration time. I made a new toy which I would like to show off. Um, it's a gravity simulation, and it simulates gravity between stars. Okay, let's get right to it. This is my grid for the simulation. It's a two-dimensional simulation, and if we place a single star, nothing happens. Before gravity can act, we need, of course, two bodies. So let's add a second to this simulation. And we'll see these two stars oscillate. We can track the trajectory of one. And of course, it only gets interesting if we add a third. And now we get some nice, interesting simulations. Here we see one star flew off, and these two are locked in an orbit. So yeah, this is the basis for the whole simulation. And where it gets really interesting is that I can simulate many more of these stars. So if we zoom out, all the way, then yeah, one of the neat things is I can actually sprinkle stars, so write stars on this grid. Let's try this out. I don't know if it's readable, but it says hello world. Of course, the patterns you write on the grid are quickly collapsing, and once you got a dense area, it's self-reinforcing, so it becomes more and more dense because of the larger forces it can create. Now the colors are just ages of the stars, so freshly painted stars. Let me show you. So if I put something here, freshly painted is blue, and red are the oldest stars. Now, what do we expect from to happen here? Basically, all these clumps that get formed tend to converge. So after a while, we'll end up with one big clump. Let's see if we can. Let's see that happen. So let me move the video here. Oh. And video back. So yeah, now it's running at roughly 100 frames per second. Okay, so the clumping is progressing. We've got 1, 2, 3, 4, 5, 6 left. These are merging, and we'll end up with one big clump. This star here is mainly influenced by this little clump here, but as it gets closer to the center, it will get probably slung away by this clump. And if the stars reach the edge of the grid, they will be removed from the simulation. Okay, so let me clear the grid here. So if I paint, let's take a white brush. If I paint a circle like this, what do we expect? We expect to see the same clumps forming all around, which will then fall towards the center. Now, so how can we get something more stable that doesn't immediately, let's say, turn into a amorphous blob in the center? For something stable in space, you actually need orbits, which we will do next. I can also simulate a black hole in the center. Let me toggle that on. Pressing B on the keyboard. Now there is singularity here in the center, which has 20,000, the mass of 20,000 of these stars. So it will rip apart any structure that is here. So how are we gonna create something more stable? We have to make it orbit. So we've got a black hole here, and if we spawn new stars with the initial velocity orbiting the black hole, it will be more stable. So if I like this, then we'll see that because this ring is orbiting the black hole, it will be longer lived than a ring that is not orbiting, because it will be sucked up by the black hole immediately. And this can survive a bit longer. Of course, once you get clusters in the ring, those clusters will clump more and more together. Here's one cluster being torn away towards the black hole. So yeah, orbits it's what adds more stability. I can take away the black hole and we'll see the stars just now spin off out of the simulated world, so out of the grid boundaries. Okay, let's put it back and clear it. Let's spawn a whole bunch of them, a big field of stars, and because it's spinning, it does not immediately collapse. We will see this ring here getting denser and denser, because initial differences in density are reinforced. And the closer to the center of the black hole, the higher the velocities. And this one is remarkably stable because its velocity is so high. It will take a lot of other stars to disturb its orbit around the black hole. But if eventually it will escape and get flung off. Okay, so our solar system is situated in a spiral galaxy. Now, these spiral galaxies are a bit of a conundrum. It's an unsolved problem in science. We do not know where the spirals come from and why they are there, because the spirals should not be stable. So let me demonstrate. So if I were to make something resembling a spiral here, oh, sorry, let me redo that. I need to add velocities to those. So let's make them orbit the black hole. So here we have a spiral galaxy orbiting a black hole. Now the problem is that the outer arms are rotating slower than the inner arms. So what this galaxy will do, it will wind itself up. So any spiral galaxy should soon dissipate because it winds itself up, and this is what cosmologists call the winding problem. There are a few theories about what is causing these arms to be stable, but yeah, it's still an open problem. So let me do that again. So if I clear it, if it were just to paint across here, oh sorry, let me redo that. I need to create it with velocities. So if I create this rotating cross, it will turn into a spiral by itself, and the spiral winding gets more and more extreme until it's no longer a spiral. So yeah, it's unknown where this is coming from. So these were clusters. I just painted them without any initial orbital velocity. So they'll just be drawn straight to the center of the black hole. Now if I create something with velocity like this, then it will be able to survive longer before being pulled into the black hole. And it was kind of cool to see it getting ripped up. Get sucked in. So yeah, this was the cluster I created with orbital velocity, so it's still going around the black hole. Let's put one opposite of it right here, and maybe one here and here. So yeah, so if we follow one of the stars, we will see what path is taken. So yeah, as you can see, these here are still surviving. If I create something that has no orbital velocity. Let's put it here. Then it will not survive very long. It will start moving towards the black hole. And let's observe that phenomenon. Oh, where did I? Our tracked star got slung out of the grid. So yeah, I can change the size of the particles to smear them more out over the screen like this. Okay, let's do that another time. Let's watch them fall into the black hole. Let's turn off the grid. This got ripped apart. This one is next. Yeah, it's quite satisfying. Of course, if I were to take away this black hole for a few seconds, let's see what happens. I mean, these clusters still have their initial momentum, so they'll continue traveling towards the center, but if I spawn something new, for instance here, it will be attracted to these clusters, but no longer to the super heavy black hole, so it should survive a bit longer. Okay, maybe something about the technology behind it and the performance. So if you see here, there are roughly 30,000 stars. To compute how, so potentially each star has an effect on any other star, right? So that's like 900 million interactions, and which would mean solving that equation for gravity 900 million times. So how can we do that at well, a few hundred frames per second actually? We can only do that by using approximations and optimizations, and I will talk a little about both. Let's first take that equation. Where do I have that equation? Yeah, so if you have two masses, the gravity force depends on both of the masses multiplied. but also the distance between them. And the distance scales linear with 1 over r square, which means that if something is twice as far away, the gravity force will be a fourth. And if something is 100 times further away, it would be 10,000 times less. So gravity quickly diminishes towards zero. So if we go back to the simulation, and let's say we track one particular star here. Yeah, so to compute these, there are now 23,000 left. We do not really want to compute the distances to 23,000 other stars, because that would make it an n-square algorithm and too slow. So instead, there is a spatial system. Let me enable it. So let's zoom in. So if you consider this star here, then anything nearby, like these here, influence this star quite heavily with gravity because of their proximity. So which means that we will calculate the forces for all these stars here that they have on the star we want to simulate. Now, if stars are further away, let's say all the way here, you've got a whole bunch of stars here, but this distance is so large, and because of the 1 over r square factor, the gravity force will be almost zero. Not quite, but almost zero. Depends, of course, how many stars are in this sector. Now, to accelerate the computations, what I do is I just pretend, instead of like the 20 stars we have in here, we just make one representative or aggregate, and this aggregate basically has the mass of all these and the average of their position. Now this is of course an approximation, because if you would add all the gravity forces from all these 20 stars, you would not get the same as this aggregated star. You will underestimate actually the force, because these will have a much stronger effect than these because of that r square factor. And as we get closer to the star that we are simulating, this one, remember we're calculating the forces for this star here that's being tracked. As we get closer, we group fewer and fewer stars together, or actually smaller and smaller regions. So in this region, we use this representative, and as we get closer, the aggregation fields get smaller and smaller. So let me zoom in here. So in this sector here, we have this bunch of stars, and we replace it with one aggregate here. So this cuts down the amount of work from the square of 17,000 now, it's now 17,000 stars, to n log n, so basically 17,000 times the log of 17,000, which is a lot smaller number. So that's the approximation part of the simulation. That still doesn't make it fast enough. We also need to optimize it, and for this I wrote some code that uses the vector unit in the Intel processors, and these vector units, it's called AVX, and they basically do operations on 8 values at the same time. So there's, for instance, a multiplication operation which will take 8 floating point numbers and 8 other floating point numbers, multiply them all, 8 pairs, and store the 8 results in another register. So doing 8 stars in one go, let's say we're doing these bunch of stars, then if we do them 8 at a go, you pretty much get an 8 times speed up. Because my compiler was pretty bad, my hand optimized AVX actually was a factor 18 faster. So I factorized the code and it was 18 times faster as what the C++ compiler could get out of it. This is running on Linux, by the way, on a 4-core Haswell processor. And so the next step of the optimization is take that AVX code and basically run it on every core. And for this, we just divide all the work. All the cells are divided over the cores. So yeah, that's pretty much it. Let's do some more painting in this world. Let's switch this off. Maybe put the grid back. Clear it out. So yeah, there are different brush sizes. I can paint with or without momentum. So if I hold the Alt key and I paint something here, this cluster has a it's not much orbital velocity because there's no black hole here. But if I put a whole bunch of stars here, and now paint something here, we will give it an initial orbital velocity so it doesn't immediately collapse into here. It will slowly go around like this. So yeah, the brush sizes. So we can do narrow painting or broader. Let's put it. Oh, I exceeded. So yeah, my simulation only draws 30,000 stars at the moment. Even though it's simulating more now, the render engine just stops at 30,000. So this is why part of the grid is missing. I should be able to delete some stuff. Let's see, holding down the X key, I think. No, Control. Yeah. Okay. Okay, now it's back under 30,000 again. And I can also spawn them one at a time. Let's put one little star in here. Oh. I do not know why it immediately turns red. That's a bug I have to fix. Okay, let's follow this one, see when it shoots out. It should eventually. Yeah, there it went. Okay, yeah, I think I'm gonna leave it at this. Thank you for watching. I will eventually put this up at itch.io so you can play with this yourself. And okay, thank you, and until next time.